So I've been working on my Taca WebAssembly multimedia runtime again. And I had mentioned it in a video about a year ago when I first talked about it, and I haven't worked on it a whole lot for quite a number of months. And I've actually rebooted it a couple of times recently. It was also nice of Disney to name their Scar character Taca, although spelled not quite the same as I'm doing. Meanwhile, to explain sort of the point of Taca, it's like a fantasy console or an app runtime. For a different example, there's the Wasm 4 fantasy console, which is still built on WebAssembly. And I've contributed to this in the past. It's a great project. It purposely has limited size and colors, and that's a design choice, and it's a fine one. There are others out there also, like the Null Zero runtime. And they've reached out to me some to see if we could work together, although I'm not really sure how to coordinate properly, so far we haven't. But they do a great amount of 2D graphics, for example, here, and are definitely ahead of me in terms of the WebAssembly interface types support, or WIT support, for defining their API. I need to do that at some point, but I have not done it yet. There's also the Orca runtime, which is primarily focused on a strong foundation for building applications outside of browsers based on WebAssembly. And they have a lot of things I don't like, a user interface framework. So that's a quick run through of some of the other projects out there that are vaguely similar to Taca that I'm working on. And some of the differences are that I'm trying to build on a GPU graphics foundation, and also I'm trying to make sure it works well in the browser and on native, which also means that I need the runtime to be small. So for example, here we see in my web version that I have downloaded less than 256K out of less than 800K total of the product. And a majority of this cost is interpreting spir-v shaders. So I'll get to that a little bit later. Anyway, I found that I was going a bit slow and wasn't really happy working directly with the web GPU API because it's very much a lot of work on the part of someone using it. So I switched a little bit to mini-quad, which runs well both on native and in browser, and provides a relatively simple API to work with for making applications and games. However, there are some things I wasn't quite happy with about it, which is why I rebooted it a second time recently. And I considered basing it on Good Game Easy, at least for the native side. GG Easy also has a web-based version that's not exactly compatible but close, and is based on mini-quad. But for now I chose to piecemeal the native side together myself as well. Although I've definitely been looking at the kinds of dependencies GG Easy uses. So just like my thing I announced a year ago, for the native side I'm using winit and WGPU. Though I had some temporary distress watching some memory leaks happening, which conveniently they fixed after I started my reboot while working on this project. Anyway, so fundamental to WGPU is also the ability to translate shaders. So you can input either spir-v, which is a binary format for Vulkan, or WGSL or GLSL, where WGSL is the standard being used for building web GPU, which still is not finished yet. And notice for GLSL input, it's only very recent versions. Then it can output any number of these things. So in the new version of Taca, I'm loading spir-v shaders, which then I just use directly in WGPU, however they end up translating it to the backend needs. And for the browser version, I've manually written all of the browser support myself in TypeScript, and I'm translating to GLSL with Naga. And this is by far the heaviest weight thing that I have in the web runtime. Maybe spir-v to GLSL can be done in a lighter weight fashion, but Naga is what I got right now. Other options out there don't look as easy to work with as this one. And I'm using Naga in the browser by compiling it again to WebAssembly. So let's take a look at some code. Just a very quick survey of what's going on. And hopefully I'll have more interesting things done in the future. So here's my example app that I've written in Zig. My next example I'll probably write in a different language, just for the sake of variety and making sure things work well across the board. And I don't know if you remember my last example, but this is way shorter. Here's my setup code. And here's my code that's happening on every frame. Then I just have some struct definitions. Okay, so I set the title, I print a message, I build an RGB triangle, then tell it what vertices to use, I create a shader, and some state I can manage across the frames. Notice I'm not actually saving any of these locally inside of my app. I've decided for the sake of making extra simple things that I'll remember inside the runtime which buffers and shaders you've made, and if you only have the minimum number of them, I just apply those automatically. Note here also that I have not told it the layout of things. I haven't said to the runtime what these points mean. It just sees them as raw binary data. Same thing applies for the uniforms down here. I just say, apply uniforms, and I give it a native struct, which is just binary data. And so on each frame, I get the state, which includes the size of the window so I can make sure I have a good aspect ratio inside of my shader. I give that aspect to the uniforms. I give it the number of frames and where the mouse pointer is at. Then I draw my triangle. Again, I haven't even said what buffers to use because I only have 2 buffers in the first place. And then I tell it how many characters I want to draw out of my text. And I up my frame count. For now, I presume I'm going to run at a consistent 60 frames per second. I'll probably have to make that variable in the future. The shader just does this, which I've written in WGSL and compiled to spir-v using Naga. I receive the position and color, and I calculate a sine function for the scale of the triangle, and I divide by that scale, which is why it gets crazy huge, and I apply the aspect as well, and I send the position and color back out for my vertex shader. And to simplify the usage of this, when I just sent the binary data along, for example in the uniforms or in the buffers, I actually inside of my runtime inspect the shader and read what kinds of attributes and uniforms it has so I can automatically interpret that data inside of my runtime code. That's why you don't have to do it manually in your Taca app. I'm going to give some options to set up manually to control some details on it, but out of the box, I make some guesses of the defaults you might want. In the fragment shader, I do some highlighting based on the distance to the cursor, and then I produce an output color. So again, that's what this app looks like here. Not very interesting, very simple proof of concept so far. And we can also run it natively. Yay, it does the exact same thing. And we see here the output high from Zig, which also went out to the web browser console. We can also go full screen here. And I get a much higher frame rate actually on the native version than I do on the web version. But I'm manually pushing that down to 60 FPS at the moment. And for a look at the size of the native app, we see here about 10 megabytes for the link time optimization version of it. Presumably, this will get bigger as I add things like audio support and everything else that's going to be needed. And here's my building of the Zig app. This is the version we're seeing right now, which is 1621 bytes of an application. I'm also working on a different demo that does some manual handling of additional buffers, but I haven't finished that demo yet, nor the support for it. And in building, here's what I do. I use Naga to build the WGSL into spir-v, and then I use spir-v opt, which is a different Vulkan utility, to shrink it, because spir-v turns out to be a very bulky binary format. And I build the Zig to Wasm, then I use Wasm opt to shrink it, and in part motivated by spir-v shaders being so large, but it could apply to all your other data as well. I actually support LZ4 of your entire Wasm binary, and then I call that a .taca file. So for example, if we want to see that spir-v shader here, oh yeah, that's useless. I probably want to do XXD. Notice here a whole bunch of zeros, like half the data is zeros. Very not efficient format. I've considered actually going and taking these spir-v shaders and running them through the same kind of integer shrinker that Wasm always uses, and then also LZ4ing everything in the end. And I use LZ4 because it pretty much can decompress as fast as it can load data. So there shouldn't be any delay in terms of using an app when it's LZ4 compressed. Although I'm also presuming that everything you care about in your app is still going to fit in a single binary, because even though I'm not intending any kind of size limitations like we get, for example, in Wasm 4, I want to promote a mentality of everything is right here where you need it, and it loads and runs fast. Meanwhile, for now, I've only defined the Taca API in Zig. I need to put it into WebAssembly interface types, or WIT, so I can easily translate it to other languages as well, or at least have it as a reference point for languages for which there's no WIT bindgen support. And then, like I said, I've implemented a TypeScript backend that runs in web browsers and implements the Taca API. Most of it is in TypeScript, so I've implemented Taca twice actually. Everything I do I implement in TypeScript and in Rust as 2 separate implementations with a little bit of code reuse. For example, I use third-party LZ4 decompression in both of them. In both cases, it's a Rust library, and I'm using it through Wasm in the browser. And I'm also using Naga, like I said, for interpreting the spir-v and translating it to GLSL. It's here somewhere. And I've used Wasm bindgen that I demoed in my previous video to have access to this third-party Rust code from my TypeScript code. I've also done some manual work to be able to draw text using the 2D context for the HTML canvas, and then convert that into textures and draw the textures to the screen so we have text available. And here's my bindings on the Rust side. Again, like I said, except for the Naga spir-v handling and the LZ4 decompression, everything right now is two completely separate implementations of Taca. And here's an example of using Naga to read information about the shader so that I can initialize Wasm GPU in a more automatic fashion. And then back to my Zig app. For the sake of proving we can change the program here, let's change one of the points on the triangle. Get a little more of a sharp triangle, I guess. And let's change the shader so that instead of dividing by the scale, we'll multiply by the scale. And let's see if we can build it here. Yay, we built it. Happened to be slightly smaller with those changes. I don't know why. Compression works in mysterious ways. And I guess even the original size got a little bit smaller somehow. Okay, so let's look at it in the browser. And reload the page here. And apparently it didn't do what I thought it would. Oh, that's because I'm looking at the remote one. Let's look at the local one instead. Yay! So now we see it sharper than before and shrinking to 0 instead of magnifying to infinity. Just to make a point that I'm actually using that Zig and WGSL source to create an application that Taca is interpreting. And also let's run it in the native runtime for fun also. Yay! So my intention here is that the native runtime is the more interesting one. And I've seen it work correctly out of the box on one of my Windows machines and failed on another Windows machine, and I don't know why. But so far, the web-based app has worked correctly on all the machines I've tested, including my phone. Anyway, that's ignoring a lot of the details of stuff. It does get tricky. And then the fun thing is that I've made a container that you can use from Podman or Docker that includes all of the current tools necessary to build what I've made so far. And I've got a GitHub workflow that then does this and builds that demo automatically to run in the browser. So you can see all the things that are necessary to make it work because I've got this stuff up and going automatically. And so some things that are improved from last year is that now Taca runs in a browser. It didn't before. And I'm using spir-v instead of WGSL as my input shader format. And I'm trying to make it as easy as possible for the user making apps for Taca. Oh, and also the whole idea of drawing text is something new, because I think I absolutely need the ability to draw text. Probably also need the ability to connect text into accessibility things so you can have capabilities for using applications for people, for example, who have low vision. Anyway, so once I get things a little more generalized, though, with just buffer handling, maybe a little bit improved text handling, it should be possible to make a demo game. And that's what I'd like to do for my next demo, and probably from ideally both different application languages and different shader languages. I might try HLSL with Microsoft's DXC compiler next time. Anyway, I hope this has been fun, and if you liked the video, be sure to subscribe. Bye, y'all.